Hello folks, welcome to the next live episode of Differential Equations. Today we're going to be doing something very exciting. As you can probably tell by the graphic here, we're going to be finding the total mass of a variable density wire. So let's go ahead and get started. The first thing we're going to do is assign some variables to this wire. Okay, so what does a variable density wire mean? It means you have a wire with, well, varying density. Some parts are thicker than others, so this part of the wire might be very thick, and as you go down to the bottom, the wiring might get much thinner. And so we actually have an equation to represent the density of this wire, and we'll get to that shortly. So here's the problem statement formally. We have a variable density wire whose density is proportional to its distance from the line y equals 1. And the wire we're dealing with has a circular shape. So it has a shape that looks like a circle, and we're going to be focusing on the first quadrant where y is greater than or equal to 0. We want to find the total mass of the wire in the first quadrant, and not only that, we want to find the total mass given that this is a variable density wire whose density depends on its distance from this line, y equals 1. Alright, so how are we going to get started with this problem? How do we find the density of this wire? Knowing that the density is proportional to its distance from this line, y equals 1. Well, if we know the density is proportional to something, we know there's going to be a proportionality constant, right? So there's going to be a constant k of proportionality times, we know that the density is proportional to what? Well, it's proportional to the distance of the wire from this line. So the density is proportional to the distance from this line to the wire. So if we have a particular point here, the density would be determined by this distance, let's call it d. And so our density would simply be the distance between the wire and this line. Instead of d, I'm going to use y, since that's a better variable to represent everything here. So let's use y here. Okay, so we have the following. The density is proportional to k times 1 minus y. So what can we do from here? Well, the first thing you should notice is where should the density be thickest? Let's get an idea about the problem before we start making any calculations. Well, notice that if y is equal to 1, then the density is 0. So where is y 1? Y is 1 exactly at this point. So at this point, we should have no density. And where is the density maximum? When y is 0, right? When y is 0, we're only focusing, by the way, in the upper quadrants, in quadrant 1 and quadrant 2. And you can see that when y is 0, I have the maximum density, right? When y is 0, I have a density of k. And that would happen at these 2 points. So I know that my density should look something like this. So my wire is very thick over here. It gets less and less thin. It gets more and more thin around here. And then it starts getting thicker again as I approach the x-axis. Right? So this is how the density of my wire is distributed. And I also know that my wire is symmetrical around what axis? My wire is symmetrical around the x or the y-axis. Which one? Well, it's a circle, right? It's symmetrical around the y-axis, as you can see over here. Since we're only focusing on the upper quadrants, it's symmetrical around the y-axis, and so my center of mass should actually be on the y-axis itself. So how are we going to find not only the mass but the center of mass of this circular wire? Well, first we have to recall the center of mass formula. And what is that? Let's head over to the next board. Recall that the center of mass is given by the following formula. And I'm going to explain that formula in just a bit. It's given by the center of mass in the x-axis, called the x bar, and the center of mass along the y-axis, called y bar. So for x bar, what is our formula? Well, it's as follows. X bar is simply the mass I have along the x-axis times the radius of that mass away from my origin point divided by my total mass. When I say it like that, it sounds complicated, but I'm going to explain in just a bit. So my center of mass in the x direction is going to be none other than my x variable times my mass in the x direction. So that's given by rho ds, where rho is the density function and ds is just a little bit of length or curvature or arc length. So when I multiply a density function by a length function, what do I get? I get mass. And when I multiply mass by a radius and divide that by the total mass, well, then I get my center of mass in the x direction. So we take that, that's going to be our x center of mass. And what's our y center of mass going to be? Our y center of mass is very similar, but as you can imagine, instead of x, I'm going to be using my y variable. So I'm going to have 1 over m times the integral of whatever mass I have in the y direction times the actual mass of that object. So rho ds. So this is the formula we're going to be employing here. Now, what is the motivation behind this formula? How can you understand this formula? First, let me straighten this formula out. I think it's a bit rotated. So we want to understand what's going on here. We don't just want to memorize. So it seems like I cannot rotate it. That's fine. So how can we get a sense of how this formula works? Let me proceed to the next page and I'll show you. Imagine you have a seesaw, like on the playground. So you have a seesaw like this, and there's a fulcrum, right? There's a kind of center point of the seesaw. Now, there's nothing on the seesaw right now, but let's say I put some object. Let's say I put a little mass here. It doesn't have to be a circle, just a mass. And I'm using a circle here just for show. Let's say this mass is m1. I'm going to call it m1. And let's say it's some radius r. So from the center. So this is the center. And let's say this object is some distance r from the center, r1. Now, what will the center of mass of this seesaw be? Well, obviously it would shift from the center a bit to the left, right? A bit in this direction, a bit in the direction of where this mass is. In fact, we can calculate how much the center of mass would shift. We can say that the center of mass is simply as follows. We know that the center of mass would shift more if your mass is heavier, right? If your mass is greater. So of course, the center of mass in the x direction, whatever the formula is, it has to be proportional to whatever your mass is. But we also know that the farther the mass is from this fulcrum, the less the center of mass will deviate from the center line. So that means the center of mass would actually be, in the x direction, would be inversely proportional to the radius, right? Inversely proportional to the radius. So we know if the center of mass is proportional to the mass, inversely proportional to the radius, well then, if something is inversely proportional with something else, you gotta multiply it, right? Just like F equals ma, where inertia reduces them, a greater mass reduces your acceleration, you multiply m and a. In much the same way, a greater radius reduces your center of mass deviation. And so you're gonna multiply these two quantities, so you have mr, not m over r, mr, okay? Because you can imagine as the radius goes up, the center of mass would deviate less, okay? But if I actually divide it by r, well then it would actually deviate more, and I don't want that, okay? And of course I want to take the weighted average of all of this, but in this case I only have one object. But if I had more objects, I would divide by the total mass, which would be m, capital M. So let's say I do have another object, just for illustration purposes. Let's say I have a second mass around here. And I'm going to put this mass a little bit above. Let's say this mass is a bit bigger. So you can tell this mass is much bigger than the other one. And this mass, we'll call it M2. And let's say it's a radius R from the center. Okay? Let's actually draw it from the center to here. So let's say this is R2. Well then, what would my center of mass be in this case? Well, it would be pretty simple, right? It would be, let's make this more accurate. It would be the sum, sigma of the masses times the distance they are away from the center divided by the total mass. And just to make this as accurate as possible, we're going to put some indices from I equals 1 to n if you have n masses, and we're going to assign that index to each of these, m sub I, r sub I. So this, ladies and gentlemen, is the formula for center of mass. And so now we're going to employ this formula for finding the center of mass of our little circular wire. So recall our circular wire. Our circular wire center of mass is given by this formula, and this formula is strikingly similar. In fact, it's exactly the same as this formula. In fact, if I take the limit of this formula as n approaches infinity, I'm going to get the center of mass formula. Believe it or not, let's do it. Let's do it. I'm going to have the limit as my number of pieces get infinitely small. So what's happening here is that I have this wire, I have this circular wire, and to find its center of mass, I'm creating some slices, and I'm calculating the mass of each slice times the distance of that slice from the center. So here's the mass of some slice, mi, and here's its radius from the center. And I'm adding up all of those masses times radii and dividing by the total mass of the wire to find the center of mass. And so what I'm really doing here is to get a really good approximation for the center of mass of this little circular wire, I've got to take the limit, right? I've got to take the limit and make the number of little pieces infinite. So I'm going to take the limit as n approaches infinity of the sum from I equals 1 to n of m sub I times r sub I divided by my total mass m. Now my total mass m here is going to be a constant, right? So this right here is going to become an integral. This little thing here is going to become an integral. It's going to become the integral of what's my mass? Well, we'll figure that out later. And times r, and don't forget this is a constant here, this divided by m, so we're going to pull that out just to make our lives a bit easier. 1 over the total mass. And now if we go back here, you'll see that I have rho ds. And what is ds? ds is another way to write dr dt times dt, where dr and ds are the same thing. So I'm just going to write dr here because we're finding the integral with respect to my radius. So hopefully the live viewers can see that. So if I calculate the formula for my mass, what is that formula going to be? Well, remember, mass, density, is simply mass over volume, right? So that means mass is simply density times volume. But here we're dealing with a two-dimensional object. It doesn't have a volume. Instead, it has an area or a length, right? So instead of volume, we're going to employ length. So it's going to be the density, which we'll now write as rho to avoid confusing it with the differential. We'll write the density function as rho because now the density is no longer constant. It becomes a function of your position times your volume, right? Now I'll add this complexity later, but you get the idea. We have a density function times my length. So we'll call a little bit of length dl. Actually ds, since it's not a straight length, it's a kind of arc length, if you will. Okay, that's great. And so now I know that my density function is actually a function of my position, x comma y. And we're multiplying that with a tiny bit of arc length. Seems like we've got a jumping new visitor here in our audience, but let us continue. So we now have derived the formula for, well, it seems like our audience is a bit excited now, but we have now derived the formula for our center of mass. in both the x and y directions. And we've used none other than nothing more than simple physics. So now that we've got a basic idea of what we're gonna do, let's go ahead and do it. Let's go ahead and find that center of mass. So first, let me finish up my formula here. I now know that my formula is simply gonna be 1 over m times the integral of what's m over here. Well, I just derived that m is rho ds. So I'm going to have rho x comma y ds. And where did I get ds from, you might ask? Didn't I have dr before? Well, ds is simply another way to write ds dt times dt, where ds is just another way to write dr, because they're both representing a bit of length, right? Okay, that's great. So we have the formula we need for the center of mass. Now let's go ahead and find it. So to find the center of mass, what are we going to do? Well, we know that the mass is given by the integral of my density function times a bit of length. And recall that this little length here, what is this going to be? What is this guy? This guy is none other than dr dt times dt. And dr, again, is the same thing as ds here. So no need to get worried about that or fret over it. But the reason I wrote it as dr dt is so that it's really obvious to you, or hopefully it's straightforward to you, because nothing is obvious here, but hopefully it's straightforward to you that dr dt is simply another way to write r prime of t, right? It's another way to write your velocity function. So we have our velocity function times a bit of time, dt. So let's go ahead and continue this. My mass, let me put it over there. My mass is my integral of my position function, of my density function. What is that going to be? Well, recall that rho is simply a function of y in this case. It's k, my constant of proportionality, times 1 minus y. So this is the density function that I have to keep in mind while I'm doing my integration and all my other math. This is the density function. In fact, I'll put this on the right hand side so we can keep that in mind while we integrate. Let's highlight this in yellow or light green because it's pretty important. Okay, and let us move onward and forwards with our integration. So instead of rho xy, I'm going to have k, oh, that is an awfully big highlighter, k times 1 minus y dr dt times dt. Okay, well, y, what is y? I'm integrating with respect to t, so obviously I can't have any y's here. Well, y itself is a function of t, because we can parameterize our curve. How can we parameterize our circular wire? Well, the parameterization for a circle is none other than cosine and sine, right? Cosine of t, comma sine of t, right? And so now we can replace y over here. We can replace y over here with what? I'll have my total mass is equal to, k is a constant, so we'll pull that out. Hopefully you can see that here. Times 1 minus, my y is simply the y component of my parameterization, which is sine of t. So I'll have sine of t. And what is dr dt? Dr dt is simply my velocity, right? And so what is dr dt? Remember, we're actually finding the magnitude of dr dt, so I should put brackets around it. So this is not absolute. Hopefully the folks in YouTube can see us and the folks in the live. So we have our magnitude of the velocity vector, which is simply 1. So instead of dr dt, instead of this funny business, I can simply write 1, which is equivalent to writing nothing at all. And I'll write dt here. So I have my mass is k times the integral of 1 minus sine t dt. And what are my bounds going to be? This is a definite integral. Well, remember, I was just trying to find the center of mass over the x-axis. So that's going to be where y is positive. In other words, when we go from theta is 0 to theta is pi. Not 2 pi, pi, because 2 pi would also allow the negative y value. So we only want from 0 to pi. Okay, so now let's go ahead and integrate this. we're going to have as follows. K is simply a constant, so we'll have K times t from 0 to pi minus sine of t from 0 to pi, and close the parentheses. So what is this going to be? Well, K is simply the constant. We'll have that on the outside. Pi minus 0 is pi, minus sine of pi is 0, so is sine of 0. So we'll just have the following for our mass. We'll have sine of pi is, actually let me write this out for the viewers who might not understand this math. We'll have sine of pi minus sine of 0. Okay, sine of pi is what? Sine of pi is 0, right? Because you're on the x-axis. Sine of 0 also 0 because you're on the x-axis. So we have K times pi for our mass. Now let's go ahead and check, and let me explain through the process of checking what we did here. To find the mass, the total mass of my wire, what did I do? Well, I had my dr dt, I had my dt, I had my function k times 1 minus y. I had the following for my mass. I had k, which was the constant, so I pulled it out, times 1 minus sine of t. Where did that sine of t come from? Well, it came from the y component of my parametrization, times dt, and then I simply had k times t from pi 0 to pi minus sine of t. But that's where the mistake is, right? Because the integral of sine of t is not sine of t. What is the integral of sine of t? It's minus cosine of t. But I have a negative sign here, so we've got to make this positive cosine of t. So it's a good thing I was reviewing this, because I would have made a mistake on live camera if I weren't. So we have the following. We have plus cosine of t from 0 to pi. So this is simply what? K times, again, pi, plus, here we have something different. Cosine of pi is what? That's negative 1. Cosine of 0 is what? Cosine of 0 is 1. But we're subtracting them, so it's minus 1. And so I'm going to have K times pi minus 2 for my total mass, for the total mass of my variable density wire. And let's go ahead and box that in. Oh gosh. Hopefully we can get a thinner marker. There we go. K times pi minus 2 is the mass of my variable density wire. Okay? And no units here. We're not doing physics. We're doing differential calculus, differential equations, and a bit of vector calculus as well. So now that we have the mass of our object, what should we do? Well, head back to what we were doing just a bit before. Recall that now that we have the mass, all we have to do is integrate all of this. So let's go ahead and get started on that business. So I know that the center of mass of my wire in the x direction was going to be 0. So x bar is automatically 0 from the beginning. Because my wire is symmetrical, since I'm considering only half the wire, it's symmetrical around the y-axis, right? So then the center of mass on the x-axis should be 0. But we've got to now find y bar, which is given by 1 over m, 1 over my total mass, times the mass of my object, rho ds, times y. Alright, so let's do it. How are we going to do this? Well, the first thing you should consider is my mass. We found the mass in just the previous slide was k times pi minus 2. So let's go ahead and plug that in for mass here. And so we have y bar is equal to 1 over k times pi minus 2 times the integral from 0 to pi. Remember, we're only considering the upper half of the circle, a semicircle if you will, times y. What is rho? Rho was the density function. I'll take you back if you don't recall that the density function was constant of proportionality times 1 minus y. So we're going to have times k times 1 minus y. Just for clarity, I'm going to rewrite ds as dr dt times dt. Okay, now if you're a clever observer, if you're a keen observer, you'll note that these k's cancel out, right? These k's cancel out. So we're going to have, for our integral, replacing the y variable here with the y component of my parametrization, with the parametrization of my curve, which is what? Which is sine of t. So let's go ahead and head over to the slide. So y bar is equal to 1 over pi minus 2 times the integral from 0 to pi of sine of t times 1 minus sine of t. dr dt we know is 1 from the previous slide. If I head back here, recall that dr dt was 1. So I don't need to do anything there. So let's head over to the next slide. So I'll simply have dt here. And so what do I have now? I have this integral. All I have to do is this integral to find my center of mass in the y direction. So I have 1 over pi minus 2 times the integral. Well, let's actually do this step by step, because this integral is a bit more complicated. So I distribute. I'll have sine of t minus sine squared of t dt. And so what comes next? We have y bar. Actually, I don't know if I should continue it on this slide. So let's move on to the next slide. Or actually, let's continue it over here. So coming over to the right hand side here, I'll have y bar is equal to 1 over pi minus 2. Hopefully you can read this. And I'll pull my mic in this direction. So 1 over pi minus 2 times the integral from 0 to pi of sine of t minus sine squared of t dt. Okay, so how am I going to find this crazy looking integral? Well, this integral is not as tame as it may seem, because we cannot use the power rule on that second sine squared. So what are we going to do? Well, let's first do the easy one. So the integral of sine of t, the integral of sine of t is no more than cosine of t minus cosine of t. And if you check that, the derivative of cosine is minus sine. Minus minus makes it positive. So let me write that a bit nicer. Minus cosine of t from 0 to pi minus the integral. Let me bring it here. Minus the integral of sine squared t dt from t is 0 to pi. All right. So how are we going to calculate the integral of a square of a trigonometric function? Well, here's the formula you've got to use. Okay, you've got to use the hyperbolic functions, or at least think of it that way. Remember that cosine squared of a function, cosine squared of t is equal to what? I'm sorry, not cosine squared of t. Cosine of 2t is equal to cosine squared t minus sine squared t. Right? And you might ask, why? Why, Rifat? Why is it that way? Well, remember that cosine of a plus b is given as the following: cosine of a times cosine of b minus sine of a times sine of b. And correct me if I'm wrong, because I am the guy who always forgets trigonometric identities. But as far as I recall, this is the trigonometric identity right here. And so if I have the same value for a and b, in other words, if I have 2t, something like 2t, I'll have cosine of t times cosine of t minus sine of t times sine of t, right? So then I'll end up with this function, which might remind you of the hyperbola, right? Hyperbola also has something like that. So how can we use this to our advantage? Well, remember that we can rewrite cosine squared t as something else. We can rewrite it in terms of sine. So cosine of 2t is simply 1 minus sine squared of t minus sine squared of t. This sine squared of t comes from here, and this 1 minus sine squared t comes from cosine squared of t. Okay? So now I can just go ahead and simplify this. So cosine of 2t is 1 minus 2 sine squared of t. So bringing this over to the other side, I have 2 sine squared t is equal to 1 minus cosine of 2t. And dividing both sides by 2, I end up with sine squared t is simply equal to 1 minus cosine of 2t all over 2. All right, so now that I have sine in terms of a double angle function, I believe that's what it's called, that now we can go ahead and really simplify this out. So to do that, I'm going to head over to the next slide, if you don't mind. So we have the integral. Here's what we know. We know that sine squared of t is equal to 1 minus cosine of 2t over 2. Hopefully I wrote that correctly. 1 minus cosine 2t over 2. Indeed, that's what it was. So that's what we have. That's what we know, and what we want to know is the integral from 0 to pi of sine squared t dt. So let's go ahead and calculate this integral. I'm going to have what? Well, I'm going to replace this sine squared t with this. And a fraction with no powers is much easier to deal with than a trigonometric function with powers. So I'll have the integral from 0 to pi of sine squared t, which is 1 minus cosine of 2t. And I'll pull out that constant of a half out, and with respect to t. So let's calculate this integral here. Doing some simple u substitution, I have u being 2t, and so if I calculate this integral, I'll be left with half of, what is this? Well, the integral of 1 is simply t, if I do it with respect to t, and I'll have plus half of sine 2t. Now, what I'm really doing here is guessing, right? I'm guessing what my integral is going to come out to. Now I'm going to check to see if my guess is correct. So sine of 2t, this is the antiderivative. If I take the derivative of this, I should get back what the integrand is. So the derivative of half of sine of 2t is cosine of 2t times 2. So I'll end up with cosine of 2t. But this has a negative sign here. So what if, I think I should be putting a negative here. Let's see if that's right. So I'll have t, that makes sense. And I have the derivative of sine of 2t over 2 is simply cosine of 2t times 2. The 2's cancel out, and so I'm left with sine of 2t. I'm left with cosine of 2t. That's looking good. And this is from t is 0 to pi. Okay? And of course no plus c, this is a definite integral. So we're going to have half, what is pi minus 0? That's simply pi minus half of what? Half of we got to be careful here. So half of sine of 2 pi minus sine of 0. Okay? So this is half of pi minus half times sine of 2 pi is 0. Sine of 0, 0. So we're left with what? Pi over 2, is that it? Pi over 2. Now, and so what is this going to work out to be? I'll have half of t from 0 to pi minus half of, let's see, the integral of cosine is sine of 2t. But if I just do sine of 2t, I'll get cosine of 2t times 2. That's going to cancel out. So I need another divided by 2. So that's here. And that's going to go from 0 to pi. So if I work this out, what's that going to be? For my y center of mass, well, I'm going to have half of pi minus 0, okay, that's one element of it, minus half of, what are we going to have here? In fact, not just half times a half is a fourth, and we're going to have sine of 2 pi, is that right? Sine of 2 pi minus sine of 0, minus sine of 0. Okay, so that's going to work out to be 0 on the right hand side. So we're just going to be left with half pi. And so now, ladies and gentlemen, it seems like we have found our center of mass in the y direction. Recall that the center of mass in the y direction was going to be this. So if I go ahead and plug in, I now know that the center of mass in the y direction is going to be 1 over pi minus 2 times minus cosine of t from 0 to pi is going to be what? That's going to be minus cosine of pi coming over here minus negative cosine of 0. Okay, that's going to be one aspect of it. And then I'm going to subtract minus sine squared blah blah blah, sine squared of t dt. And I know now that that's going to be pi over 2. Is that right? Yeah, pi over 2. So this is going to be minus pi over 2. So let's work this out. We're going to have 1 over pi minus 2 times cosine of pi is what? That's negative 1 times negative is 1 minus, what's cosine of 0? If I remember correctly, that's 1. And minus 1 makes it 1 minus pi over 2. So we're going to have none other than 1 over pi minus 2 times 2 minus pi over 2. And let's see what this simplifies out to be. I'll have 2 minus pi over 2 over pi minus 2. And this is going to work out to be, let's see, 4 minus pi over 2. Is that right? Yep, that should give me 2 over pi minus 2. So my final answer is none other. For my y center of mass, my final answer is 4 minus pi over 2 times pi minus 2. And there you go, ladies and gentlemen. Wow, that right there is my final answer. So my center of mass is, if I condense everything into one answer, my center of mass is going to be none other than as follows. X bar, comma, y bar is equal to 0, comma, what's my y bar? Let's see, 4 minus pi over 2 times 4 minus pi over 2 times pi minus 2. And there you go. That is our final answer. Thanks for watching this episode, sponsored by Brilliant.org, and we'll check you out next time.
Embedded plus MKO plus scaffolding equal learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO, and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.